So, as promised, I'm going to go over this sheet and these various shapes that have been presented here. I've done my best to try to draw out some of these shapes to talk about here. So first of all, a very long, thin-walled cylinder with uniform charge density sigma naught. One thing that I want to point out here, I've drawn a cylinder here. It's not very long. Very long is kind of a euphemism for infinite. Nothing is really infinite, but we'll just assume it's very, very, very long. And assume it's basically infinite. So when we're looking at something very long, here we have sort of ends that I've drawn, but we can imagine this just goes on forever. So right here, this is just going to go on forever. And try to make it the same color here. We'll just say this keeps on going for as far as we can see. And so that's really how we want to imagine this. And what this means then is we never really have to worry about the ends. We're just going to have the cylinder that goes on forever. Okay. Well, what that means is if you think about a point that's above the cylinder, somewhere up here maybe, well, any point to the left of that is going to create an electric field that's up and to the right. Any point to the right is going to create an electric field that's up and to the left. That's going to cancel each other out to give us a field that is directly up, away from the axis of the cylinder. And so in this particular case, what we're going to have here is we're going to have an electric field that is directly away from the axis of the cylinder. So we can imagine that this cylinder will have an axis like that. Maybe I'll make that dashed. Okay, that's the axis. So we have the axis running down the middle of the cylinder, and the electric field is going to be pointed directly away from that, or in other words, in the s-hat direction. Because this is a uniform charge density, we know that we'll have this cancellation. We get an electric field in the s-hat direction, so that takes care of this first step. We can also say if we spin the cylinder around the axis, then nothing would change, that it would look the same no matter how we spin it. So phi doesn't matter. Phi will not impact the electric field. We could also say that if we were to move along in the direction of the axis, if we set up that axis to be our z-axis, or moving in the z direction, nothing would look different either because this is uniform. But if we move in the s direction, away or toward the axis, then we would see something that would be different. So for this case, we have an electric field that's in the s-hat direction, and it only depends on s. So we would need a Gaussian surface that would be in the s-hat direction for some parts of it, and perpendicular to the s-hat for other parts. And if the Gaussian surface has an area vector in the s-hat direction, then that means that we need to have a uniform value of s. Well, one thing that I just realized I forgot to mention in the previous video is the direction of the area vector is something that's very important. So the direction of the area vector is perpendicular to the surface. So it's known as the outward normal. And normal in this case meaning perpendicular. So this is something that we'll be looking at in your homework a little bit about an area vector. But if we need a surface that has a uniform value of s, well, that will give us a spherical surface that would be sort of at this point here where we want to know the field, and then we would have a surface that it curves around at the uniform value of s, and then comes back around this way somehow, and then curves back like that. So we'd have something that looks sort of like that. This is a very bad drawing, but hopefully you get the idea. That this is going to be a finite cylinder that has a radius s wherever we want to know the field. Now, this curved surface, sort of like the label of a soup can, that's the surface that has a uniform value of s, and it has a direction of the area vector in the s hat direction. The end caps have certainly not uniform s because it goes, this must be a solid end, to be able to get a closed surface. So we have another surface over here that's going to be sort of an end cap, another surface over here that's a circle, an end cap over here. And what we have with these is that the area vector, though, so I'll say that for, oops, didn't need to do that. For this surface here, the soup label, we have an area vector that's in the s hat direction. And down here it would be something like this, also in the s hat direction. For these end caps, the area is perpendicular to this. Perpendicular to this surface would be directly to the left, or in this case, the z hat direction. Perpendicular to this surface over here would be directly to the right, or I guess that would be the negative z hat direction, for defining it that way. So these end caps would contribute nothing to the total flux because the electric field just sort of skims along the surface. It does not pierce the surface. It does not go in or out of the surface. And so those end caps contribute nothing to the electric flux. We only have to worry about this central surface, like the soup label. So in this case, Gauss's law is useful. You would use a finite cylinder for a Gaussian surface. And that would also work if we wanted to know the electric field in here, inside this long, thin cylinder. We would choose a Gaussian surface that's a cylinder that's just on the inside. We would have something like that with, again, circular end caps. That's kind of hard to draw, but that's the general idea. So we have these circular end caps and the cylindrical surface that's inside there. All right, so number one, yes, it'll work. Number two, I'm going to delete some of these things here to make some space. Be able to think about this a little bit more. So number two, we have this hockey puck, also a cylinder. So it's natural to think, okay, great. Now we just talked about how we can use this for a cylinder. Well, let's use it then. Well, we have to be careful because one key factor here is that when we want to know the electric field, if we're straight up from the middle, then using the same kind of symmetry arguments we've used before, we would get an electric field that's straight up. If we're over here directly on the side, we use similar arguments that every point above will create an electric field down, every point below will create an electric field up, to add together to give us straight to the right. Okay, well, that works out pretty well. But if we go somewhere else, somewhere like over here, we could say, okay, well, the charge is below this point and to the left of this point, so this is going to give us an electric field that's up and to the right. Right? It has to. But the big question is, how much up? How much to the right? If I go right here, I might expect it to be a little shallower of an angle. That didn't work very well. Expect it to be a little shallower of an angle because we're closer to this side. If I go over here, I might expect it to be a little bit steeper of an angle because we're sort of closer to the top middle over here. But I don't know exactly what those directions are. And there's a problem right there. If I don't know exactly what the direction is, then I can't use Gauss's law because I can't do that dot product and we're violating this first criterion. So for this hockey puck, not going to work. We'll exit out. For this hockey puck, we can't know the exact direction of the electric field. We know an approximate direction, up and to the right, or up and to the left if we're over here, down to the left over here, whatever. But since we don't know the exact direction of the electric field, then we can't use Gauss's law. This one is not going to work. And it's because we have this finite cylinder of charge. All right, next one. A thick-walled beach ball, charged at the top half is positive, bottom half is negative. Tell you what, I tried really hard to draw this in a good way, and with the tools I'm using here, it's just not working out. So I'll try sort of what I had intended, something like that, which will go like this, and we'll make it thick, and hopefully that'll do something for us. So that'll be the positive half, and then we'll draw a negative half. And for good measure, I'll make it a different color. We'll make that one red. And you know, this probably looks awful, but this is what we're going to deal with. All right, so again, if we want to know, if we want to talk about the electric field, if we go directly above, then if we're closer to the positive half, then we can say that it's going to be away, so it's going to be up. If we're close to the negative half, we can say it's going to be toward the negative half, like that. That didn't work so well. Let's try this again. Go toward that negative half. Nah, whatever. So, did that work? I don't think it gave me the arrow that I wanted, but that's all right. So, in this case, get it toward. If we go straight over to the side, we're going to get something that's straight down. This is something that you did in class as well. Let's go back to that. And over here, again, we'd also get straight down. This is being very strange. That's all right. Ah, there we go. This one. Haha, okay, let me switch that up, because that should be straight toward. Okay, so we'll get something that looks sort of like this. All right, so if the electric field sort of goes up, curves around, and comes into the bottom. So we're going to get electric field that sort of does something like this, right? Go back to like that. And we know that it's going to be going sort of in that direction if we were drawing the field lines. But that means if we go over, say, over here, we could say that it's going down and to the right. And over here, it's going down and to the left. But we can't say for certain how much down, how much to the left. And that's the key problem with this one as well. So with this one as well, it's not going to work for us because at these locations that are not along the equator of the sphere or along the poles, if it's anywhere else, we don't know exactly the direction of the electric field. And if we can't know the exact direction of the field, we can't choose a good Gaussian surface, because we can't choose that integral, or that dot product, to be able to pull E out of the integral. So, not going to work in this case. All right, let me clear up some space here for the next one. Next one, solid sphere has a cavity carved out of it. Well, the way to think about this is that a cavity is really like taking a completely solid sphere, like this on the left, and subtracting a tinier sphere from that. So we have a big sphere minus a little sphere equals this thing here. And so In that case, the question you have to ask yourself is, could I use Gauss's law on each of these individual pieces? The original solid thing and the thing that I'm taking away. Well, for the sphere, the answer is yes, and that's something I talked about in the previous video, that if we have a solid sphere that's uniformly charged, and that's what we're told here, that has this uniform charge density, with that uniform charge density, the big sphere, we can use Gauss's law. The little sphere, we can use Gauss's law, both of which will use a spherical surface, which means when we put them together, that's just going to be superposition. And so we can still use a Gaussian surface for that. No problem. Interesting thing here is that if we were to take this cavity and make it not concentric, have the cavity over here, we could still use Gauss's law for each individual piece and then add the fields together. But we could not use Gauss's law for the whole thing by itself. So there's no, because the sphere, the Gaussian sphere you use for the big thing would be centered at the center of the big sphere, and the Gaussian sphere used to determine the electric field for the little sphere would have to be centered at the center of the little sphere. If those are in the same place, then everything's great. We can use just one Gaussian surface. But if they're in different places, then you need to be careful about how you're applying Gauss's law and incorporate superposition. So for this one, yes, no problem. We can use it and it's going to be great. But if instead the cavity is a cube, then we have a little bit of a problem, because a cube suffers from the same problems as the puck here did, in that if we were to go sort of off at near the corner here, say right here, you'd say, well, it would kind of be up and to the right, but there's no way of knowing exactly how much up and how much to the right. So a cube is not a valid object to be able to apply Gauss's law, because we can't know the exact direction of the electric field. And that's no good. So in that case, we cannot use Gauss's law for the cube, which means we cannot use Gauss's law for the cubical cavity, which means we cannot use Gauss's law for this object here. So again, it's because we can't know the exact direction of the electric field. And that's really a key component. If you have a shape where you can absolutely with certainty know the direction of the electric field everywhere in space, then you're pretty sure to be able to use Gauss's law. I can't necessarily guarantee that, but I can't think of any cases where that would not be true right now. All right, last one. So here we have a very large sheet of charge, and it follows this sinc function, which is sort of a weird function, if you can picture this. So this function, if we draw some axes here, axes like this. So this function looks something like this. It starts at the origin. I'm going to try to get it close to the origin, and actually scratch that, excuse me, I need to revise that. It starts up at a value of 1, and it's a sine function, so it oscillates, but it's divided by s, so the oscillation gets smaller and smaller and smaller as it goes. So it's an oscillating function that decays with distance. And so as this goes outward, imagine this is rotationally symmetric because this is S. So we would have a positive spot in the middle, followed by a negative spot, negative ring, and a positive ring, negative ring, positive ring, negative ring, going outward. And so what we'd end up with is these various rings of charge that are all concentric. Now that seems like a very symmetrical orientation, but because this is a large sheet, we have to think about, we'd have kind of some region of positive charge and then a region of negative charge, which means if this was a sheet, I'm sort of mixing my my representations here because I'm trying to picture if we had a sheet here and it was positive and then negative and then positive and negative and positive and negative, and right now I'm going to be imagine this as the red indicates positive charge and the blank space in between indicates negative charge, something like that. But it also gets weaker and weaker and weaker. So that's the important thing to recognize as well, is that as this goes outward, it gets weaker. So that would be the thinning charges there. And the same over on the left. So for a point directly above the center, there's charge on the left, there's charge on the right that is symmetric and balances out, and so you could have a nice electric field going straight up like we've seen before. That looks something like that. But for over here, there's really strong positive charge here, but to the left, but there's no strong positive charge on the right. Over on the right, it would be weaker positive charge. And with all these different oscillating from negative to positive, if you go somewhere in between, right near the cusp between negative and positive, you might get something that's actually going over to the right. But then somewhere in between there, it has to transition, and then over here going from negative to positive again, maybe that one is going to the left. So, oh boy, that didn't work too well, did it? Let's see if I can get it going to the left, huh? There we go, going to the left. And somewhere in between, it's going to be going up or down. Yeah, if you're right in the middle there, maybe at some point it's sort of going downish. But we can't really know exactly how. Oh boy, that's a bad one. I'll just get rid of that. So we can't know exactly how it's going up or down or to the left or to the right. And because of that, we can't use Gauss's law. So there's another case that with this non-uniform charge density, we can't use Gauss's law. Sometimes a non-uniform charge density can use Gauss's law. It all depends on how it's distributed. In this case, we can't. So I hope my explanations here have made sense. If you have any questions, please let me know. I'm happy to talk about this more, and I apologize for the bizarre drawings. So I'll finish this up by saying this one, no good. So the ones that work out are the ones that have charge densities that are highly symmetric and that don't have any sharp corners. That's really what we're looking for here. We need charge densities that have a lot of symmetry to them, like the long cylinder or the sphere. Those are good, but they can't have any sharp corners, like no short cylinders, no cubes. Even though those have a lot of symmetry to them, those corners cause electric fields that we can't know the exact direction. So I hope this has been helpful, and please let me know if you have any questions.